X-ray fluorescence, otherwise known as XRF. Origin and development of X-ray fluorescence. Willem K. Röntgen is credited for discovering and utilizing X-rays. He was a German physicist in the mid-19th and early 20th century. He won the Nobel Prize for his discovery in 1901, and the notoriety of his discovery led to the widespread commercialization of X-rays starting in the 1950s. Two key people who laid the foundation for X-ray fluorescence spectrometry and spectroscopy are Charles G. Barkla and Henry Gwyn Jeffreys Moseley. Charles G. Barkla discovered the connection between the atomic weight of a sample and its radiation of X-rays. Henry Gwyn Jeffreys Moseley, with the use of X-rays, took part in numbering the elements that we know of today, and observed the relationship between energy and atomic numbers. Theory of X-ray fluorescence. A photon, or the absorption of a light wave of increased energy, can cause an electron to be ejected from its orbital and be replaced by a higher-level electron. The identity of an element can be determined by finding the wavelength of the photon, or X-ray light emitted by that particular element. Applying the theory of XRF. In order to categorize the emitted X-ray spectrum into according wavelengths for each element present in a sample, a wavelength dispersive spectrometer can be used. To measure the intensity of the emitted beams, two types of detectors are commonly used: gas flow proportional and scintillation. Gas flow proportional is commonly used for measuring long wavelengths, and scintillation is commonly used for analyzing shorter wavelengths. The value of the proportionality of each element can be compared to the known composition of rock and mineral standards. Using this information, major and trace elements in geological materials can be easily analyzed. Pros of XRF. Emission of fluorescence in samples provides a powerful tool for analyzing, which is now utilized by commercial instruments. XRF is well suited for large samples larger than 1 gram. It can be used to test a various range of elements from sodium to uranium. It can test solid, liquid, and powdered forms of samples. XRF is a relatively non-destructive instrument compared to other technologies, which is ideal in the field of archaeology. XRF is relatively cost-effective for its extensive list of abilities, and there are portable spectrometers along with the original standard systems now available. Most importantly, XRF is used in a wide variety of applications, such as, but not limited to, mining and collection of various geological samples, soil surveys, igneous sedimentary and metamorphic petrology, and in the field of archaeology, manufacturing and analysis of glass and ceramic materials. Cons of XRF. 1. This technology requires complex instruments to aid in detection of tested samples. Because of this, X-ray fluorescence is known to decrease efficiency present in photon excitation. 2. XRF technology cannot test samples less than 1 gram. 3. Some commercially available instruments are limited in their ability to measure precisely and accurately elements with the atomic number less than 11. And 4. XRF cannot specifically determine variations among isotopes in an element.